Okay, awesome. Good. All right. So today we are going to discuss more about concurrency control. The last time we have been discussing about a couple of specialized topics around locking. We have discussed, for instance, about deadlocks. So here we had discussed about how to detect them or how to avoid them. Then we have discussed about phantoms, which is this additional anomaly where I am retrieving a set of objects from the database based on predicates. And when running the query twice, then I get suddenly different results because other transactions inserted something. We have discussed how we can avoid that using indexes. And we have discussed about locking in tree indexes, where you can use the generic locking protocols, but that is inefficient. So instead, you want to use a specialized locking protocol. And we have seen how we can minimize the number of locks that we need to hold at the same time when accessing an index. Now, the final topic around locking that we will be discussing, this is multi-granularity locking. After that, we're going to switch to discuss about concurrency control methods that are not based on locking. First of all, let's discuss about multi-granularity locks. And the motivation for multi-granularity lock is that there is a trade-off about the granularity of locks. At the very, very beginning, when we started discussing about locking-based concurrency control, we had an example protocol that was very simple, and it just locked the entire database. So only one transaction was able to operate at the same time. Later, we have discussed that granting more fine-grained locks on single tables or in single rows and single tables provides you with a higher number of transactions that can execute at the same time. So it's probably good for performance. The drawback of that, on the other side, is that if you have very fine-grained locks, then transactions typically need to a lot of those fine-grained locks in order to do what they want to do. And each lock request and lock management also means a certain overhead in the lock manager. And if the lock manager has to manage lots of very small locks on many objects in the database, then that might actually become a performance bottleneck. So there's some motivation for granting fine-grained locks. There's also some motivation for granting more coarse-grained locks. And it is difficult to say which of those works best in general. So with multi-granularity locking, we don't have to make that choice because we can dynamically choose between obtaining locks at different granularity. So if a transaction wants to read most of the rows in a table, it may just get one lock on the entire table. But if a transaction only wants to access one specific row in a large table, in that case, we can get a lock specifically for that row. And multi-granularity locking allows you both types of locks. The big challenge here is to make sure that we grant those locks consistently. So if one transaction has obtained a lock on the entire table, we cannot give out any locks for specific rows anymore, which conflict with the first lock. And making sure that we grant those lock requests in a consistent manner, that is the focus of what we discuss in the following. So in general, we assume that we have a hierarchy of database objects. So here there would be at the root of that hierarchy the entire database, and then it splits up into single tables, and for each table it splits up into pages, and each page splits up into different tuples again. So that is the hierarchy of database objects, and with multi-granularity locking, we can obtain locks at different layers of this hierarchy. Now, the way in which we make sure that we don't grant any conflicting locks is by introducing new types of locks. those are those intention locks. We have two types. We have the intention shared lock and we have the intention exclusive lock. And what that means essentially, if you acquire an intention shared lock on some object in that object hierarchy that we have just seen, it essentially means that you intend to acquire a shared lock on one of the contained objects. So if you have an intention shared lock on a table, it could, for instance, mean that you intend to acquire a shared lock on one of the pages in that table or on one of the tuples on one page of that table. And similarly, for the intention exclusive locks, if you acquire an intention exclusive lock on a table, for instance, it means that you intend to acquire an exclusive, meaning a write lock for instance, some tuple or for instance, some page within that table. And we will see in the following why using those locks prevents bad things from happening when granting locks at multiple granularities. Now, this is an overview of which of those locks are compatible. We have started out with only two types of locks, the shared locks, meaning locks for reading data, and exclusive locks, meaning locks for writing data. For shared locks, we can grant the same shared lock on the same object to multiple transactions. For exclusive locks, that is not possible. Now we've introduced two more types of locks, so it gets a little bit more complex to keep track of which combinations of locks are allowed and which combinations are not allowed. Here you see the full overview. I guess many of those combinations are intuitive, so you always see the green check mark if the combination of locks is allowed, meaning if the lock manager could grant those two different locks to different transactions on the same object. Now, for instance, clearly we can grant the same shared lock on the same object to different transactions. That's why we have a tick at the corresponding position. One question that I often get about this matrix is, for instance, why is it that intention shared and intention exclusive locks should be compatible? Because as we know, shared locks and exclusive locks are not compatible. So why is this version of the locks more permissive? And so let's perhaps quickly discuss that point. So for intention exclusive locks, it essentially means that you want to acquire an exclusive lock on some contained object. So if you get this on a table, it means you might want to get an exclusive lock on a row. On the other side, the intention shared lock means that you want to acquire a shared lock on a contained object. So that could be also a row. But the point is that if you grant an intention shared lock on one table to a first transaction and an intention exclusive lock to a transaction on a table to a second transaction, at this point, things could still go well because maybe the first transaction is interested in a different row than the second transaction. So we don't know at this point whether two transactions are really interested in the same contained objects or in different ones. And as long as they're interested in different contained objects, like different rows contained in a table, everything is fine. All right. And the general rules to use those intention locks is before you can request a shared lock on an object, you first must have obtained intentioned shared locks on all the ancestors of that object in the object hierarchy. So if you want to acquire a shared lock on a row in the table, you first must acquire intention shared locks on the containing page, on the containing table, and potentially on the containing database. Similarly, for intention exclusive locks, if you want to acquire an exclusive lock on a row, for instance, you first need to acquire intention exclusive locks on the containing page, table, and so on. All right, so you need to acquire those intention logs before you can acquire logs that you actually want. One little detail about the point where you release those logs again. It is important that you release those intention logs not starting from the root of the object hierarchy, but rather starting from the leaves of that object hierarchy, and release them in this order. Otherwise, there's a small time frame in which inconsistent logs could be granted if you do it, if you release those logs the other way around. And now let's make it a little bit more concrete why those intention logs can help. For instance, imagine this situation here. Transaction number 1, drawn in green, wants a shared log on table 1. On the other side, transaction 2, here drawn in pink, wants an exclusive log on one specific page in that table. And clearly, those two logs are mutually exclusive. So if we use the system with the intention logs, then here you see the intention logs that would be acquired. So here at the beginning, both transactions acquire intention logs on the entire database, one intention shared and one intention exclusive. But those two logs are compatible because at this point, we don't know whether those transactions are maybe interested in completely different objects that have nothing to do with each other, except that they're both located in the same database. Now we continue to table 1, and for table 1, transaction 2 wants an intention exclusive log, while transaction 1 has already arrived at its goal and wants to acquire the shared log directly. And at this point, the intention exclusive conflicts with the shared log. This is why the situation that we grant inconsistent logs to those transactions cannot happen, because we're using intention logs. I believe there might be some questions in the chat. Let me quickly check that out. And those intent, okay, this is a great question. The question is essentially about like how long we hold those intention logs. And the thing is that, I mean, for instance, in this example here, if the, let's say that the or let's say that the second transaction goes first and maybe succeeds in obtaining the exclusive log for the page that it is interested in, and now it would decide to release those intention exclusive logs on the answer stores. Now, at that point, a transaction number 1, drawn in green, might actually proceed and acquire the intention shared log on the database and the shared log on the table. But that would be inconsistent with the log that transaction 2 has acquired. So it is very important that we do not release those logs on the answer stores, because otherwise we might grant inconsistent logs. Great question. All right. Now let me quickly change my set of slides. If there's any follow-up questions or any other questions, then please don't hesitate to put them into the chat. And there was one more question about like the benefits of intention shared and intention exclusive logs. perhaps we can even quickly go back to that one, to this example over here. All right. So now you should see the example again. And here, essentially, if we would not use any intention shared or intention exclusive locks, then the database might grant inconsistent locks at different layers of that hierarchy. Here, for instance, there's transaction 2 wants an exclusive lock on one specific page, which is contained in table 1. And transaction 1 wants a shared lock on table 1. And logically, if some transaction has a shared lock on the entire table, it implicitly means that it has a shared lock on each page in that table. So that would be inconsistent with granting an exclusive lock to transaction 2. And I mean, an alternative to intention locks would be, for instance, that transaction 1, before acquiring the shared lock on table 1, first checks all the pages and all the tuples of the table in order to see whether maybe some other transaction has acquired a conflicting lock on some element within the table. But doing that, of course, is very inefficient. So the whole reason for multi-granularity locking is that we want to improve efficiency. Because of that, it is much better if the second transaction marks up not only the specific object, the specific node in the object hierarchy that it is interested in, but also all the ancestor nodes on the path from the root to the locked node in order to indicate that there is some object within the table and within the database where we have an exclusive lock. So marking up the path from the root to those objects in the object hierarchy is a means of avoiding checking overheads when granting locks to coming transactions. So there would be different ways of solving that, but via those intention locks, it's pretty efficient. All right. Does that clarify things? Okay, awesome. Good. All right, great question. And now I hope that my slides are still switching. Yeah, I believe that is the case. All right. So, so far we have been discussing a lot about locking-based concurrency control. Now, in the following, we're gonna discuss about alternative methods to do a concurrency control without locking. Now, it may seem a little bit imbalanced, the amount of time that we dedicate to talking about locking-based concurrency control and the amount of time that we'll be talking about all other concurrency control methods. But in practice, locking is perhaps the most popular concurrency control method. This is why we spend more time discussing about that. But there is various alternatives, and in the following, we're gonna see a little overview of those alternatives. So within this course overview slide, we are still talking about the transaction manager, and the relevant chapter in Ramakrishna and Gerke is specifically chapter 19.5 for those concurrency control methods which are not based on locking. Now in the following, we're gonna discuss about those 4 concurrency control methods: optimistic concurrency control, timestamp concurrency control, multi-version concurrency control, and snapshot isolation. And many of those concurrency control protocols, they have some common ideas to them. For instance, many of them, they use timestamps in one way or in another one, but in general, they are different. And you might find that for specific databases and workloads, one of those works better than the others. and it is difficult to say a priori which one it is. Now, first of all, let's talk a bit about optimistic concurrency control. Now, in a way, locking-based concurrency control is rather pessimistic, because before doing anything, transactions always have to acquire those locks in order to avoid any conflicts before they actually happen. Now, that means that we have to pay with overheads for lock management, and depending on the locking variant, we might also have things such as deadlocks, for instance. So we are avoiding conflicts between transactions, but it comes at a cost. And so in a way, it is a pessimistic strategy that assumes that those conflicts between transactions are somewhat likely. So transactions will probably sooner or later try to write to the same object, or one transaction tries to read an object written by another transaction. Now, the premise of optimistic concurrency control is kind of the opposite. It's saying that those conflicts, they are rather unlikely. So let's maybe just proceed and do things and just assume that nothing bad will happen. And then at the very end, we will verify whether our assumption was actually justified. If it was not justified, we have to pay the overhead of, for instance, aborting and restarting the current transaction. So with optimistic concurrency control, we essentially trade locking overheads for potentially higher overheads due to aborts. We will discuss about the pros and cons in a little bit. So let's first get some overview of how optimistic concurrency control can work. In order to make it work, we first of all need to do some bookkeeping. For each transaction, we need to keep track of the objects that the transaction has read and the objects that the transaction has written. This is what we call the read set and the write set in the following. And based on those read and write set, we can validate whether any bad conflicts happened or not. Now, in more detail, the execution of a transaction consists of 3 phases. First, the read phase, then the validation phase, and finally the write phase. What happens in the read phase is this. The transaction, first of all, identifies the objects that it is interested in the database. And then it essentially copies those objects into some private transaction-specific memory location. So it gets its private copy of the relevant objects in the database. And then it also executes the entire transaction on this private copy of the relevant data. There is sometimes confusion about this phase in my experience, because the official name of that phase is a little bit misleading, because it's the read phase, while in reality we're not only reading data, but we are also kind of executing the transaction on the private copy of the database. So read phase, that is the official name, that is why I'm using it here, but I noticed that people tend to get confused about that. This is why I want to proactively avoid that confusion. So read phase means reading the data, but also executing the transaction on a private copy. Now, before we can actually publish the things that have changed in the private copy of the data, we first have to validate in order to ensure that no conflicts have happened. During the validation phase, I'm essentially checking whether any other transactions have accessed the same objects that the first transaction being validated was working on. And if those changes to those other objects or those accesses to those other objects conflict with what my current transaction has done, then I actually have to abort and later restart the current transaction. So this is where optimistic concurrency control is optimistic, because it assumes that in almost all cases, this validation will check out okay, and there haven't been any conflicts in the meantime. Now, if the validation succeeds, then we proceed to the final phase, which is the write phase. And here we essentially publishing the changes from the private transaction-specific copy of the relevant data to the public overall database. So we are writing those private copy changes to the public database where other transactions can see it as well. Now that is the high-level overview of how optimistic concurrency control works. Let's discuss about the validation phase in a little bit more detail, because that is the key to concurrency control. It generally works by assigning unique timestamps to transactions at validation time. So essentially our goal is to create like a serialization order of the transactions that is consistent with those timestamps. So in the end, the database should look as if those transactions had executed in timestamp order. And also what other transactions see, which transactions sees the changes from which other transactions, that also should be consistent with those timestamps. During the validation, we essentially check sufficient condition in order to make sure that no bad conflicts between transactions have appeared. Now, we can be sure that there was no bad conflict between two transactions. For instance, if the first transaction has entirely completed before the second transaction. Now, in that case, clearly, there cannot have been any conflict. Also, we might refine that and say, we also can be sure that there is no bad conflict if the first transaction completes before the second transaction starts writing. Also, in this case, what could happen is that the first transaction writes values to objects that are read by the second transaction. So here, there could be some kind of bad influence linking the two transactions, but we can be sure that this does not happen if the write set of the first transaction, the objects that the transaction has written to and changed, is disjunct with the set of objects that the second transaction has read. So if that holds, then we can be sure that the first transaction hasn't influenced the second transaction. So here, both of them cannot have conflicted in a bad way. And as an extension of that, perhaps the first transaction completes before the first transaction completes its read phase before the second transaction completes its read phase. That means that we could, for instance, have overlapping writes in addition to the first transaction writing objects read by the second transaction. So as an extension, we also want to ensure that the write set of the first transaction, the objects it has changed, is disjunct from the write set of the second transaction. In that case, they cannot override each other's changes in a bad way. And we can also be sure that no bad conflicts have happened. So those three conditions is what we can verify in the validation phase. And if one of them holds, then we can be sure that there have been no conflicts. Those conditions, they are perhaps overly conservative in some cases. None of those conditions might be satisfied, but still everything would be okay. In those cases, well, there's some trade-off between bookkeeping and between the probability that we have to abort the transaction, even if there's no real reason for it. So typically, this provides a nice trade-off between those conflicting motivations. All right, but just so you know, even if none of those conditions is satisfied, you might still actually have a good case without bad conflicts, but nevertheless here, we would abort a transaction in this case. So at the validation phase, we are verifying that with all the other transactions currently in the system, at least one of those three conditions is satisfied. And if so, we can allow the currently validated transaction to proceed to the write phase. One simplification that people often make in implementations in practice is that we combine the validation and write phase essentially into one single phase. Then we need to make sure that only one transaction can be in this combined validation and write phase at the same time. So while one transaction validates and writes, other transactions are blocked from access to the public database. If you do that, the conditions simplify. You only need to consider the first two of them. This is simplification often encountered in practice. All right. Of course, there is some overheads. I'm saving the overheads for locking, but now I need to keep track of the read set and the write set. And of course, if my validation phase does not check out, then I have to restart, to first abort and then restart the current transaction. And if conflicts are quite frequent, that is a high source of overhead. Also, depending on implementation, there might be a critical section where I reduce concurrency because only one transaction can operate at the same time if it is in this combined validation and write phase, for instance. So there's pros and cons. Probably you want to use optimistic concurrency control in scenarios where conflicts are rather infrequent. Another non-locking based concurrency control is a timestamp based locking. So here we associate again each transaction in the system with a timestamp, and our goal is to serialize those transactions in the order of those timestamps. So the database should look as if those transactions had executed in the order of those timestamps. Now, we not only associate transactions with timestamps, we also associate objects in the database with timestamps. Each object is associated with a read timestamp, which essentially is the timestamp of the last read operation on it, and with a write timestamp, which is the timestamp of the last write operation on it. So essentially, those read and write timestamps for objects are set based on the timestamps of those transactions. So if a transaction with a certain timestamp reads an object, then the read timestamp of the object is updated to the timestamp of the transaction, because logically, essentially, each transaction executed instantaneously at its assigned timestamp. And this is why we update read and write timestamps from the transaction timestamps. Now, we have to essentially check a couple of conditions whenever a transaction wants to read and write objects in the database. Those conditions essentially tell us whether if we proceed with an operation, whether we are still consistent with the timestamp order of the transactions. Now, here I outline those rules that we have to verify, and if a transaction tries to do an operation that would violate one of those rules, then this transaction is aborted and restarted later. So here we use TS of T as the timestamp of a transaction, and RTS of A and WTS of A. Those are read and write timestamps of the object A. And now, if a transaction wants to read some database object A, we have to abort and restart the transaction if its timestamp is smaller than the write timestamp of the object that it is trying to read. Logically, this makes sense because of the following. So if a transaction has a certain timestamp, it means that everything should be as if the transaction had executed at that time. And if the transaction had really executed at a specific time, then the version of an object that it reads must have been written by a transaction that executed before. Now, in this case, we see that the object A has been updated by a transaction with a higher timestamp than the transaction that is trying to read. That means if we would allow the transaction to proceed and to read the current value of A, we would be inconsistent with the timestamp order because the transaction should have read an earlier value of object A written by a transaction with a smaller timestamp. And because of that, if we have this condition here, it means that we have to abort the transaction trying to do the read and restart it with a higher timestamp. All right. Now, on the other side, what happens if a transaction tries to write an object in the database? So logically, if a transaction executes at a certain time and writes a value for an object A, then all transactions that are executing later than the current transaction should read the value written by the current transaction, because then logically it is as if everything had executed in transaction timestamp order. Now, if we see that the timestamp of the transaction trying to do the write is actually smaller than the read timestamp of that object we are trying to write to, it means that another transaction with a higher timestamp has already read the current value of object A. And that means that allowing the transaction to proceed with the write operation would mean that we are becoming inconsistent with the timestamp order, because had the transaction really executed at time t, it would have written the value read by the later transaction, but that has not happened. All right. So one interesting case that we might also think about is what about multiple writes on the same object? And for instance, we could think about aborting and restarting a transaction if the transaction timestamp is smaller than the current write timestamp of that object. So because logically, if transactions had really executed in a timestamp order, then the final write to object A would have been executed by the later transaction. But here we are essentially trying to override the later value with an earlier value. So a naive way of doing this is to just say, okay, in those cases, we abort and restart the transaction. Okay, and actually, before I continue, okay, there's one question here in the chat. Wouldn't aborting T and restarting still give you the same problem? Okay, that is a great question. And actually, it depends on the timestamp that you restart the transaction with. So what we are doing is, if our current timestamp ordering does not succeed, if we would try to restart the transaction with the original timestamp, we would run into the same problem again. So that's a great point. But what we are doing instead is that we are restarting the transaction now with a higher timestamp. And this is why things change. So in theory, even with the higher timestamp, we might again have to abort and restart the transaction a couple of times, but at least now we have the chance with the higher timestamp that the thing which led to the abort before won't happen again. Great question. And here, okay, that is the question about the case at the bottom of the slide here. So I already said that one possibility to deal with this case would be to abort and restart the transaction. But since I marked this up and formulated it so tentatively, you can imagine that there might be a different way of doing things, and that is the so-called Thomas write rule. This rule applies in the case that we have just seen, where the timestamp of the transaction trying to do a write is smaller than the current write timestamp of that object, which conflicts with serialization order. So clearly we cannot allow the transaction to proceed with the write. But on the other side, we don't really have to abort the transaction either, because we can just say this transaction would have written some value to object A. Analyzing the read timestamp, we can see that the value of object A written by the transaction would never have been read. So essentially, we can just act as if that write operation had never happened. So we don't necessarily have to abort the transaction trying to do the write. And that is what the Thomas-Wright rule essentially states. It states that we can ignore outdated writes and don't even need to abort the transaction causing it. So essentially, what it does, if you consider it from the perspective of the schedules that it allows, if you look, for instance, at this first schedule here marked up in red, I have a read of object A by transaction 1, followed by a write by transaction 2 on the same object, then transaction 2 commits, and now I have still a write of transaction 1 on object A. Now, so first of all, this schedule is not conflict serializable, because here, if you see, we have a conflict on object A between transaction 1 and 2. So the corresponding graph, we would have an edge from transaction 1 to transaction 2 due to the read followed by the write. And also we would have an edge from transaction 2 to transaction 1 because of the write followed by the final write by transaction 1. So we have a cycle, and that means this schedule is non-conflict serializable. But on the other side, it would be view serializable, because here the final value of object A is written by transaction 1, and transaction 1 also reads the original value of object A. So this write by transaction 2 to object A is kind of pointless. It is not read by anyone, and it is changed again later by the first transaction. So actually, we could kind of act as if that write to object A had never happened. And at the bottom, you see the corresponding schedule. So here we just remove this write operation, which doesn't really have any effect whatsoever. And here we end up with a schedule that is serial. So actually, we could move the commit by transaction 2 even before to make that more clear. But clearly, transaction 2 doesn't have any operations anymore. Here, you only have a read by transaction 1 followed by a write of transaction 1. And those two schedules, they are view equivalent. And the Thomas-Wright rule essentially allows us to capture such cases to avoid aborts and restarts in cases where writes don't really matter. So that is an optimization to the simple handling strategy that we have discussed before. But what if W2A affected different rows in A than W1 of A? And the thing, I think there's a misunderstanding about like basically which types of objects we are granting those locks for. So that's a great question. So here we essentially assume that those objects A, they refer to things like, that could, for instance, refer to one single row. So here we are not considering multi-granularity locking. We're only considering atomic objects in our database, which typically are rows. So here, A, that could, for instance, be the row in your accounts table, which represents the account of one specific customer of Alice, for instance, right? So we don't consider multi-granularity locking. So if we have two operations on the same object A, it means that they refer to exactly the same object in the database. All right, good. So for timestamp concurrency control, we also have a couple of overheads. Like for the optimistic concurrency control, we also might have overheads due to restarting and aborting transactions in case of conflicts. Also, here we need to keep track of object timestamps. We need to keep track of the read and the write timestamp for all objects in my database. And depending on the granularity, if you're talking, for instance, about a single rows, which is typical, then having to store some values to timestamps for each of those rows, that could actually mean a little bit of space overhead. Also, there is the overhead of updating those object timestamps. Because for everything to work correctly, we need to keep track of those timestamps. Might have to recover them, for instance, during a recovery operation, which we will discuss quite soon. And also, if you're just reading an object, if a transaction is just reading an object, then still we have an associated write operation because we need to update the corresponding timestamp. And that means that we have quite a bit of additional overheads, especially because of the last point, because now every object access essentially transforms into a write operation. And better using this is a good idea in practice. It depends again on various factors, but those overheads, they make it a little bit less attractive than some of the other concurrency control methods. All right, so we might not finish completely with multi-version concurrency control anymore, but I already want to give a little intro there. As the name suggests, the main idea of multi-version concurrency control is that we keep around multiple versions of each object in the database. So the protocols that we have seen so far, they would assume one single value for an object in the database. Here we have multiple versions that are associated with different timestamps. And this example here shows why doing that can be a good idea. Here, for instance, we have a schedule which is not conflict serializable in the way in which it is written. So we have an edge in the conflict graph from transaction 1 to transaction 2 because of the write to A followed by the read of A by the second transaction. And we also have an edge from transaction 2 to transaction 1 because of those conflicting writes and reads on object B. And those two are marked up in green and blue in this schedule. Now, we would have a conflict serializable schedule had the read on object B happened before the write to object B. So if those two would be swapped. So in order to essentially get there, what we could do is that when having the read on object B, we just show to the requesting transaction an old version of object B before the write by the second transaction. So keeping around those multiple objects and choosing which version to show to a transaction is essentially a way of avoiding conflicts that are caused by reads, like the one that you see here in the example. And because of that, it might allow us to avoid some conflicts due to those reads. On the other side, of course, here now I have to keep multiple versions of an object around, which is also associated with overheads. All right. So here again, we assign timestamps to the transactions once they enter the system. And the next time we will see in more detail how we check whether transactions can proceed and how we decide which version of an object to show to a reading transaction. So we're going to discuss that in more detail next time. But the main idea here is to keep around multiple versions of an object, and that can help to resolve certain conflicts where other protocols would have to abort the corresponding transaction. All right. Thanks. And I see you again next week. Have a great weekend.